Astronomy and Astrophysics postdoctoral fellow at UC Riverside, who will be talking to us about measuring the masses of the longest period transiting giant planets. Take it away, Paul.
Great. Okay, thank you. Let me pin Colby, and then I'll go ahead and share my screen. Let's see. Oh, let's see. Okay, and then let me start here. Okay, is everybody able to see the screen? And hear me okay?
Yep.
Okay, great. Well, thank you. Thank you to everyone for being here. Once again, my name is Paul Dalba, and I am an NSF Astronomy and Astrophysics postdoctoral fellow at UC Riverside. I'd like to thank the SOC for inviting me today to speak about my work. And I would just like to thank everyone who's here making this meeting really a really fantastic time. I know that I feel a lot more connected with the community here in Southern California from being here and hearing about everybody's research. And I'm just really grateful that everybody got together and is fighting through the Zoom fatigue. It's real, I know that, to be here and learn about really cool science today. So I'm really excited to tell you about what I've been working on, and that involves exactly what the title says, measuring the masses of the longest period transiting giant exoplanets. So if I could sum up everything I was interested in, it would really be that I am trying to push the science that we can achieve with transiting exoplanets out to its extremes, to the longest orbital distances that you possibly can. And that's why I'm showing an image here of Jupiter. That would be the ideal, of course, if we had a transiting true Jupiter analog. Think of what we could do with that. Now that might be a bit extreme, but I'm going to show you the next best thing. Okay. All right, before I go too much further, I have to acknowledge my collaborators. There are many of them, and I think the best way to do it is sort of to highlight the little bubbles in which I work. The first of which is the UCR Planetary Research Lab that's led by Stephen Kane. Thank you to everyone who falls into that bubble. And I also very heavily collaborate with the TESS Single Transit Planet Candidate Working Group. And this is one of the many TFOP working groups, and that's led by Diana Dragomir and Stephen Villanueva Jr. And I'll come back to the work I'm doing with them. And then, of course, the California Planet Search and the TESS Keck survey have been very much important to the work I'm doing. So to everyone who falls into these bubbles, thank you for helping and supporting my research. All right, so one of the reasons that I'm really excited about giant planets is that they're such an inherently interdisciplinary and multifaceted topic to research. There are a bunch of different ways in which you can approach the problem of giant planets. And so there's just a couple of them. So you can study these giant planets as the planets that they are. They are indeed planetary objects. You can approach them from that side. However, there's sort of a cottage industry that studies giant planets through analogy to brown dwarfs and other substellar objects. There's a lot of, it's a very active area of research of characterizing brown dwarfs and then seeing what we can learn by analogy to giant planets, because they're a very similar class of object as far as that goes. Now, in addition to the two different types of objects, we also have the cosmic good fortune of being located near a couple gas giant planets. They're in our backyard. Of course, this is Jupiter and Saturn. We can actually go there, we can sample them, and we can study them on incredibly fine detailed temporal and spatial scales. And that's what we've done over the last couple decades. Now, the flip side of that, of course, is getting a much broader picture of the situation and focusing on exoplanetary systems. And we found giant planets in abundance and quite a diversity in exoplanetary systems. Now, when it comes to actually pursuing these different areas, I'm going to make the argument that the one that's most in need of advancement right now, that's in need of work, is indeed the exoplanet angle. Because when it comes to giant planets and exoplanetary systems, it's really an incomplete story. And I can demonstrate that by showing this figure that I'm sure we've all seen. This is mass as a function of orbital period from the NASA Exoplanet Archive for all of the known exoplanets right now. And anytime we see this plot, of course, we should all be skeptical and say, wait, there's a ton of observational biases on this plot. And that's exactly why I'm showing it in this case. I'm not going to try to make an assumption, an interpretation about the underlying population of planets. I'm instead going to talk about the biases. So for most giant planets on here, we can't get the full picture. Really, the best case that we have here are the transiting planets, and those are the ones that you see here in green. I highlight things that are more than just giant planets, but the giant ones are, of course, at the higher masses. So for these transiting planets, we can get the full picture being mass and radius. It's a pretty simple picture, but when it comes to exoplanets, that's really what we're talking about. Those are the launch pad to everything else that we want to do. Now, as you move away from the star, you're fighting against that transiting bias out to further away planets, such as radial velocity planets or microlens planets. You start to lose the full picture. In the cases of these types of planets, you can really only get mass, or perhaps just a mass ratio with the star if you can't fully characterize that host star. Now, I'll make a point here that there are many more microlensing planets that are shown on this plot. It's not a great plot for microlensing planets because its mass is a function of orbital period instead of semi-major axis. But the point remains, it's an incomplete picture once you get out past a couple tens of days to 100 days. Now, things get a little better finally once you get out to directly imaged planets. You can learn a little bit more. But right now, we're a little technologically limited of actually pushing down to cold Jupiter twins in reflected light. That's not something we can do right now for directly imaged planets. I'll come back to that later. But because we have these disparate areas of parameter space, we need something to try to glue them together. And I'm going to argue that we can start to do that with transiting planets. Although it's the least developed avenue of research into cold gas giant planets right now, but not for long. I've got a lot to explain as to what I'm doing to improve that. So I'm going to provide some scientific motivation in this talk to start it off. And I think that's really necessary anytime you combine the words long period and transiting. You're fighting a pretty severe geometry of probability there. So I'm going to give a lot of motivation for it. And then I'm going to give one case study from Kepler and one case study from TESS demonstrating what these missions are doing to actually contribute to what we know about long period giant planets. And then I'm going to spend the last little bit looking forward because doing this kind of characterization takes a long time. And I'm insisting on playing the long game here. And I want to tell you a little bit about what I'm waiting for. So for the scientific justification, why long period giant planets at all? And there are a number of reasons. I would argue that we really need to get out to the outer reaches of planetary systems and the giant planets that form and exist out there to complete the census of planetary systems. How unusual is the solar system's architecture? I show a figure here of planets that have radius measurements. And as suspected, there's not a lot of overlap with the solar system. Now, on top of that, a really fun question is where are all the exomoons? Perhaps we're just looking in the wrong places for these. We've heard we heard a talk about this at this meeting yesterday, I believe. And I think just going from the solar system alone, if we were to search for exomoons, you would look at Jupiter and Saturn and say, well, that's the kind of place to look for exomoons. So perhaps as we push out to longer period giant planets, that's where we'll find them. But the planets themselves also have significant science motivation, and especially their interiors and their atmospheres. And this is also coming from motivation within the solar system. So Jupiter and Saturn are pointing to an interior structure diversity among giant planets, it seems. Is this something we could explore with exoplanets? Well, indeed it is. So recent advances from Cassini and Juno have essentially repainted the picture of what we know about the interiors of Jupiter and Saturn. In the plot I'm showing here, it's density profile for Jupiter, and these models have been updated to account for the measurements of the quadrupole gravity moments of Jupiter. And in fact, Jupiter seems to have this diluted core that extends out to a substantial portion of its radius. And we didn't really think that was the case for Saturn, but very recent studies coming out of UC Santa Cruz have suggested that maybe that is indeed the case too. So Cassini and Juno are fantastic, but I think they're raising more questions than they're answering when it comes to this kind of science. And that's why we need context from the exoplanets that are akin to Jupiter and Saturn. And of course, we can't ignore the fact that these planets provide context for habitability studies. Is Jupiter indeed a friend or a foe when it comes to habitability of a place like the Earth, or an Earth analog planet, or any sort of potentially habitable planet? If and when we find the planet that we really think is the best case for habitability and we're doing our intense searches, we're going to want to know if there's a giant planet. And we're also going to want to be able to interpret what it means if there is or if there isn't. So giant planets paint the full picture of planetary systems. So, okay, that's why we want to go to long periods with giant planets, but why specifically transiting? Because we're fighting this geometric transit probability. It's not only just geometric, they're long periods. We're fighting the probability that we weren't going to see it just because we didn't observe long enough. Well, there's a couple answers to this question as well. First one's a little hand wavy, and it's, well, we happen to find some. there are some long period transiting planets that we know about just by chance. So for some numbers, there are 59 confirmed, mostly statistically validated, transiting exoplanets that are about greater than 0.4 Jupiter radii and have orbital periods greater than about 100 days. Sort of arbitrary numbers, I admit, but it gets us in the right ballpark of what I'm talking about. Of these 59 planets, only 21 have mass measurements. So if you're going to go and make a mass radius diagram here, you're only going to have 21 points. When was the last time that our favorite mass radius diagrams only had 21 points? This is something that we're a decade behind when it comes to this class of planets. So for these, of course, to reiterate the point, we can get the full picture, even if it takes us a while. It just takes some patience to get enough transits to know the radius, to get the mass with RVs or TTVs. And then, of course, some cold giant planets are indeed amenable to atmospheric characterization via transmission spectroscopy. That's what we learned by looking at Saturn as if it was a transiting exoplanet. So there is an end goal of atmospheric characterization for some of these planets, but we got to be patient. And also, direct imaging is not yet sensitive to these cool Jupiter twins, but once it is, it'll be useful to have benchmarks from transiting planets. Let me move on to telling you about the two surveys that I'm running. The first one is the Giant Outer Transiting Exoplanet Mass Survey, or GOTM survey for short. This is a program I have on Keck High-Res that's meant to characterize long-period giant planets that were discovered by the primary Kepler mission. And I'm showing here known planets with planets with known radii and their orbital periods. So these are all transiting planets. And I've highlighted the dozen or so GOTM planets on there as well. You can see everything's out past 100 days. Some things are out past 1,000 days. And most transiting giant planets that are out at those orbital periods are covered here by this survey. And most of them are validated, statistically validated. In fact, none of them are confirmed prior to starting the survey. And the big important thing here that's going to lead to some of the science later down the road is that these are all far enough away from their star that we can be pretty confident that they are not inflated. There's not going to be a radius anomaly going on due to this really intense radiation coming from the star. So when we make a measurement of the radius, we can take out the confounding factor introduced by the fact that the star may be inflating it. And that's really useful for interior studies. So that's part of the value of this group. Let me highlight one case study here, and this is KOI 375.01. So this is just a planet candidate, not a validated or confirmed planet quite yet. So looking at all of the Kepler data, what we have is two transits and a gap. So you can see the two transits here. There are little arrows identifying them, separated by about 990 days. If you divide that in half and look at that period of time, there's a gap. That's where that third arrow is. And there's some high cadence data right there as well, but there's a gap, and that's where a potential third transit could have fallen. So just probabilistically, this thing is likely to be the shorter, the 400 and something day orbital period. But it's a giant planet. It was bright enough to do the survey, and so we started taking observations of it. I started observing this as soon as I got to Riverside back in 2018. And the RVs were pretty boring for a while. They were sort of increasing a little bit. I couldn't tell if that was a trend. It wasn't clear what we were going to end up with on this one. But to show you what we found was that this is indeed a super-eccentric, super-Jupiter transiting exoplanet. This is the phase-folded RV as its output from a Radvel run. We have indeed confirmed the longer of the two orbital period options, so the P equals 989 days, and the eccentricity is on the order of 0.9. The most recent ExoFast fit we have for this one is actually 0.91 plus or minus 0.01. So this one's very exciting. You can see we just went through the periapse passage last month. That was when it got really, really interesting. And so now this one is something I'm super excited about. This is perhaps the second most eccentric transiting exoplanet. HD 80606b is going to hold on to that record, I'm pretty sure. But one fun little record that we're going to have with this planet is that for a transiting planet, it's going to have the longest apastron distance at 4 AU. On the other side, a periastron, it's at 0.2 AU. So what this means for this system is that this is very likely a potential failed hot Jupiter, which is a term I think was coined in a paper by Becky Dawson back in 2015. So this thing got to where it got based on high eccentricity migration. However, the periapse distance was not close enough for it to actually tidally circularize. So it's stuck there with the remnant eccentricity of its formation up at 0.91. And so that's going to be really useful to combine with the mass and also the retrievals we're going to do for the planet metallicity to understand how it might have gotten there and what that might tell us about similarly long period planets that are perhaps circular instead of eccentric. So that's all really fun. But there's going to be, and I could talk about case studies from Gotham for another 30 minutes, but I'm going to spend just the next minute talking about the expected outcomes, sort of the overall bird's eye view of what we want from this program, because it's almost done. It's been going for almost 2.5 years now, and so I need to be getting some results out on this one. So we have a false positive confirmation. If it's long period and it's giant, there's always going to be a false positive in there. We have 2 false planets, one of which was thought to be a single transit long period planet, might actually be a eclipsing binary. We're not sure. We put out a paper on that one just a couple weeks ago. It was a transit whodunit because we don't know what caused the transit. There's a planet and there's a eclipsing binary, or there's a star. We don't know which one caused the event. There's also a 118-day eclipsing brown dwarf that is sitting in the confirmed exoplanets table right now that we need to clean up. We have 2 upper mass limits for stars that are pretty faint and planets that ended up being more like Neptune's. So we'll publish those as well. We got beaten to the punch on 1 planet, and then we have 8 novel mass measurements coming out. And that's what I'm showing here in this figure. So we have planet radius as a function of mass. So this is a mass radius diagram. I show planets that I think have measurements better than 50%. So I've chopped out some of the noisy ones. I've chopped out smaller planets as well. And the color represents the insolation. So how much flux they're getting from their host star. And the triangles are our survey. And you can see they're all sitting pretty low on this giant planet mass radius diagram, which is what we expect because they're not inflated. I also put a couple of in-prep test planets on there as well, just planets that have similar levels of low irradiation. And then the solar system planets are there too. So these are going to be a really novel, unique group just because there aren't that many purple dots on this figure. But in addition to that, I'm going to throw another mass radius diagram at you here. And in this one on the right, I've actually chopped out all planets that are inflated or thought to be inflated based on limits of a paper by Sestovic et al. In 2018. This is just 1 sigma limits. So we're only like 70% confident that these are not inflated. So what we see here is that below about 0.4 Jupiter radii, we lose confidence that a lot of these planets are uninflated. So there are very few non-inflated planets in that regime, and we're adding around 3 or 4. And there's a lot of interesting comparisons to be done for all the planets on this plot, specifically the ones that are around a Saturn size, or maybe a little less, the sub-Saturns, but they span an order of magnitude in mass. Well, that must be some sort of interior difference. Can it be tied to formation? Is it just something about the core? And how do we explain that spread for planets that are about the mass of Jupiter, but have a spread that go way beyond standard structure models that are shown in red? Is that spread compositional? Can we tie that to orbital properties? Those are questions that people have been hoping to do for a while, but haven't had the sample that I'm hoping to revisit now that we do have a sample of long period planets that we can make confident radius and mass measurements for. So I also mentioned TESS, so I want to transition to TESS really quickly and talk about TESS's single transit challenges, because when it comes to long period planets for TESS, you're talking single transits. So we also have an APF program. That's APF being the Automated Planet Finder Telescope that is meant to follow up the masses for stars that are a bit brighter. And this is in collaboration with the TESS-KEX survey, with TFOP, with that working group I mentioned previously, and also with citizen scientists. And there was a paper in 2019 that suggested that indeed there are going to be a number of detections for single transits for TESS. We could expect dozens to a couple hundred of these things. So it's something that was worth focusing on. So as before, I'll present one of the exciting case studies, and this one's for HD 238894. This is a giant TESS planet orbiting at around 260 days. That's 10 times longer than the baseline that most of the sky is getting from TESS. This one was indeed observed by TESS for all of cycle 2. Its brightness is V of 9.2, its 9th magnitude. As someone who spent years working on Kepler stars that are faint, 9th magnitude is fantastic. I can't put enough exclamation points past that 9.2 right there. And I showed the transit right here. There was just one single transit in one sector. It was 24 hours long. The star is a subgiant, so that's part of the reason why it was so long. And this was discovered by citizen scientists that I collaborate with. And once they brought it to me, we put it on my APF program immediately and started collecting RVs. And so little by little, we started watching the data trickle in. That's what this GIF is showing. The preliminary data as it's trickling in. Is it turning around? Are we starting to be able to know what the semi-amplitude is going to be? Is there a trend in there? All of these questions are going through your head when you're slowly getting data on a long period planet. But after 6 months or so of collecting data, we know this thing is about 2.5 times the mass of Jupiter. And as you can see on the right, a mixture of APF and Keck data have allowed us to refine the mass, orbital period, and eccentricity. It's moderately eccentric. And one exciting thing for the system was that there was we predicted the next transit after the one that TESS saw, was set to occur at the end of August. And so with the help of Karen Collins and SG1 and a handful of other colleagues around the world, we organized a transit recovery campaign. And I found myself out in Joshua Tree with these 2 telescopes doing 5 nights of observing, which was really fun. I don't have any results to present there. We're still working through all the data, so that just has to be left as a teaser. So keep an eye out for more results from that later. So I see I'm starting to run low on time, so I'll spend the last few minutes talking about prospects for the future. Where are we going to go with this sample of planets? What's left to do as we move forward? So prospects for the future brings me back to this question: why transiting along period planets? And another answer that I didn't cover was future opportunities. These planets are amenable to advanced characterization techniques. They really are. The first one I like to think of, and I'm interested in pursuing, is Rossiter-McLaughlin measurements of obliquity, of the stellar obliquity for long period systems. I think there's a great potential to extend the dynamic range of systems that have had these types of measurements done to better piece together the evolutionary pathways of planetary systems with and also without giant planets. So the opportunities will be occasional, and once we have one, you'll probably have to tie together multiple sites, but it's the kind of rare science that is worthy of that amount of effort. And I'll revisit again the prospects of atmospheric characterization via transmission spectroscopy. I'm pointing to a paper I wrote as a graduate student where I used Cassini data to look at Saturn as if it was a transiting exoplanet. And with Saturn, you would have 60 part per million features from methane. You would have a 90 part per million feature from the large aliphatic hydrocarbon chains that are indicative of the hydrocarbon chemistry going on in Saturn's atmosphere. So Saturn, because of its low mass and fairly large size, is a great target, despite the fact that it's super cold, which works against you to shrink the scale height. So the idea that cool planets aren't going to be amenable to transmission spectroscopy isn't necessarily the case. So it's worth looking into. And it can be looked into with things like HST, like James Webb, and almost especially like Ariel, which is meant to increase the diversity of planets that have had their atmospheres characterized. So there are exciting opportunities down the road. In addition to that, coming back full circle here, giant planets benefit from multifaceted interdisciplinary approaches. And I want to spend a moment talking about direct imaging, because I think that the transiting efforts to go after longer period planets are eventually going to funnel into direct imaging observations. That'll be the thing that we do eventually, once we move past the transiting method for these. And ELTs will achieve this, 10 to the 9 contrast, 10 to the minus 9 contrast that we need to detect reflected light from mature Jupiter twins. That's going to happen. And I see the poll might have popped up. We're jumping the gun there. I'll continue. So cool or cold transiting giant planets that are transiting, they're going to be benchmarks. They're going to be interesting comparisons, and they're going to be connectors between the inner parts of planetary systems that we're learning about with the transit method, and also the outer part of systems that we're characterizing with direct imaging facilities. And also, I can't skip the fact that solar system synergy is now a huge driving force between planetary and exoplanetary investigations. And I'm really, really excited by that fact. If you were keeping an eye on the Planetary Science Decadal recently, there were really excellent papers by Giada Arney and Mark Marley talking about collaborative efforts. And I'll also point to this other paper that I wrote with Hannah Wakeford recently that discussed an exoplanet perspective for a future ice giants mission. So not only is it going to be, oh, look at this data, look what we can do for exoplanets, it's going to be, let's do some planning with exoplanets in mind to draw these two fields together. And it's going to be an exciting future going forward, I would say. So this brings me to the end. I spoke about the masses of the longest period transiting giant planets. And there are many avenues of research into this class of object, but it's time to focus on the exoplanet avenue. And that's what I've been working on. I spoke about ongoing RV programs that I'm leading at Keck and APF, and we're measuring the masses of about 24 planets here. And I'll just reinforce that these are unprecedented, the sample's unprecedented because they transit, because we happen to overcome that geometry and actually see the transit, despite their long orbits. And the fact that they transit enables a new set of scientific investigations into their atmospheres and their structure and their formation that's going to teach us more about our own solar system. So with that, thank you for your attention. Happy to take questions.
All right, I see we already have some questions in the Slack. Just a reminder, please put any questions in the Session 7 Orcus Slack channel. Also, great name, by the way, the Gotham survey. I love that. Just had to put that out there.
There were a lot of other worse names that we had to go through before we got that one.
Oh, that's great. I love that. Okay, we have a question from Juliet. Great talk, Paul. Do you think the ephemerides for these planets will be good enough to do transmission spectroscopy in the future?
So it's a mix of yes and no. For some of the ones that are perhaps the really good candidates, there may need to be a transit recovery effort that we do at some point. Thankfully, a lot of at least the Kepler ones are pretty precise. And so it shouldn't be too difficult to catch the next transit, assuming it's not happening at some point where the star is too close to the sun. But the also good piece of news is that for the really long period ones, you haven't missed too many transits since they were discovered, even back in the Kepler era. So as you're picking up uncertainty from every orbit that you missed, you haven't actually missed too many. So many of these aren't in a really dire situation. The only case when you are in bad shape is if you've only seen 2 transits and you don't know if there are TTVs, because these really long period planets can have another planet or a brown dwarf, something you don't know about that could be causing really large TTVs. Transit to transit TTVs on the order of days, and that can totally preclude an observation with JWST. So for those, you need to have a more extended observational effort.
Cool. We also have some comments that you might also want to make comments on. Stephen Kane says, love the phrase failed hot Jupiter. Sounds like an oxymoron since not becoming a hot Jupiter would normally be considered an orbital evolution success story. Do you have any thoughts on that?
No, I guess it's just whatever angle you see it as. I kind of like the idea of failed hot Jupiter. But I'm also pro cold Jupiter, so maybe I'm conflicted.
Yeah, so I don't see any other questions at the moment. So I'll ask a question. You mentioned using the solar system planets as sort of the start to trying to investigate these planets, but do you have any, maybe this is more of a philosophical question, but any thoughts about the fact that we don't necessarily see the same trends that we see in the solar systems in our exoplanet systems, and we might be looking for something that's unique to our solar system?
Yeah, I think that our comparisons are still limited. I think one of the most interesting plots, and I don't think I have a version of it here. Let me scan through my extra slides to see. Maybe right here, actually. Okay, so this is a plot about the ice giants paper that I mentioned briefly at the end, but I want to point everybody's attention to the plot at the bottom right here. This is metallicity as a function of planet mass. And so this is something you'll see in papers that have characterized the atmospheres of exoplanets and tried to understand what is the metallicity of that planet and look for trends in planet mass. And this is something that is very much indicative of core accretion theory for giant planet formation. And this plot, I think, is awesome because this is really getting at super interdisciplinary studies. And you see that really tight fit from the solar system, but it's problematic right now because it might not be fair of what we're actually comparing. So we're comparing in the solar system, generally these are condensable species that have been measured, measured from carbon, whereas in the exoplanetary systems, these are often oxygen measurements. And so, and in addition, the solar system, they've been measured at one spot at one time. Whereas for exoplanets, we've kind of gotten a global average of what these oxygen species may be. So if we're seeing different trends in the solar system and exoplanetary systems right now, in figures like this and in studies like this, it may just be due to how we're limited in both cases of the types of measurements we can make. I think it's an open enough field right now that there's it's sort of open season to just discover what you can about both types of planets and then try to draw similarities and differences at that point.
Cool. That's exactly actually what I was thinking of, was that mass metallicity trend.
Yeah, it stirs up a lot of conversation, which is good. And it all leaves us with a lot to do moving forward on both sides of the fence.
Yeah, definitely. And like you said, kind of meeting in the middle with this planetary science astronomy overlap, which is great. Cool. So I don't see any other questions in the Slack. I do see a comment from Kaylin to thank you for clarifying the paucity of microlensing points on the specific demographic plot that you showed.
Yeah.
And to thank you and others for using and citing the NASA Exoplanet archive.
Great.
But yeah, I think that's it. Thank you so much for a great talk.
Thank you.
Okay, so our next speaker is Dalar Babayan. She's a recent master's graduate from